All right, so for everyone coming in, what's up? We'll be starting shortly. Maybe wait another minute or so for people to join the call and connect to audio. Then today we'll be talking about how a computer works and computer architecture and all that stuff. But before we do that, we'll go over the weekly challenges we had this week. All right. We go ahead and get started. Yeah. All right. Sounds good. Okay, so I'm actually not going to look at these slides. And we're actually not going to look at my physics. Okay, so for this weekly challenges, we had a couple questions. So we had, what is the practice of concealing messages or information in files? What protocol is used to keep your connection to a website secure? Ping of death attacks which layer? What tool used during reconnaissance of a specific host for hacking? And what group of characters are often repeatedly used in a path traversal attack? So actually, after releasing these questions, we kind of figured out that these might have been a bit hard, and based off that, we really didn't expect you guys to get that much. But it's really just Googling. And so for the first question, what is the practice of concealing messages / information in files? We actually use these in capture the flag challenges or CTFs. And I think if you can just search up concealing information in files, and then steganography should show up. And that was the answer. And so you guys can read it on the Wikipedia page, and it's basically concealing messages in media files. And there's a bunch of tools that are available for you, to do kind of stuff like this. And it's kind of cool because you can like put a message in an image and then send it to your friend, and then your friend can decrypt it. But and then other people, it obviously can be broken very easily, but other people, if they don't suspect it, they won't know. All right. Okay. Next question. What protocol, or rather set of protocols, is used to keep your connection to a website secure? And so this is like like when you're on your web browser and you want to go to a website. So when you go on a website, we can go like google.com, and then they give you the little lock, and the little lock actually means that you're connected to Google via HTTPS. And sometimes you look at links, and sometimes they have HTTPS, and sometimes they all. Oh, by the way, if you want to actually see this, because usually it looks like that. If you press Control L, it shows up. You can highlight it as well. So HTTPS is actually built off of HTTP, which is the hypertext transfer protocol, and that basically is the protocol used for computers to connect to websites. And HTTPS is basically HTTP, but then you also add the S, which is, it used to be SSL, but now it's TLS, and TLS stands for transfer layer security, right? I think it's transfer layer security. TLS. And basically TLS is a form of, let's go to the Wikipedia page. So TLS is the form of encryption that cryptographic protocols that give you a secure connection. So if you're on an HTTP website, it might not be that secure, and it's definitely not that secure, and you might get like your information stolen. But a HTTPS website, like even Wikipedia, ensures that you're having a secure connection, and it's hard to connect or hard to get hacked. Or people still here. All right. So next question. Ping of death attacks which OSI layer? I'm pretty sure if you just Googled the question, it'd give you answer. Oh, there you go. Layer 3. And so ping of death attack, we'll probably talk into this more later, but OSI layer is basically a model, a conceptual model of how the internet works. And so there's these 7 layers. And we'll talk about definitely more in the later, but for now, you can just know that it's like this model that is this conceptual model set up for connecting to the internet and things like that, how the internet works basically. And so we'll just talk about the 3rd layer. So there's a bunch of layers: physical, data link, network, transfer, application. Physical layer is, well, physical layer is like just physical, like your actual wires, cables, and whatever. And 7 is like application layer, where it's like your actual software, like your Chrome browser or a website you're accessing, or even games that you're or software or whatever. And so it goes from physical, which is like, just physical stuff, to application, and slowly builds up. And the network layer is okay, the network layer is the layer that the ping of death attacks. And ping of death is basically sending a packet file. We'll talk about it more later, but packet that comes in, and it's so big that it basically overloads the system, and the system basically doesn't know what to do with such a big file. All right. Okay, we need to go faster. All right, what type of tool is used during reconnaissance of a specific host? Basically, when you're trying to hack into a host, you want to first figure out what's happening, what ports are open of the host, so how you can connect to it, and port scanners are what you use. And then path traversal attack is when you're trying to break it, or basically when you try breaking into a website, or finding more information, or information that should be hidden away, but is revealed, and basically you're allowed to look through the files. You use the // so period, and then forward slash backslash I think a forward slash, and then and that's basically, it lets you go back into the parent directory. So if you'd use enough of those slashes, you're hoping that you go all the way back to the top directory, the root directory, where a lot of info like passwords and memory can be hidden, and you shouldn't be accessing those. All right, so those are the challenges. If you guys have any questions, you guys can feel free to ask them. But yeah, these challenges weren't easy, but they could also, you could learn, it's kind of just to get you thinking. All right, so now on to the actual presentation. So today we'll be talking about how a computer works, and this is kind of more related to computer science and less cybersecurity, but some fundamental knowledge that everyone should know when going into this field. All right, so that's the walkthrough, and I think Jason will hand it over to Jason.
Yep, so starting off with computer architecture, we'll be going over the motherboard. So the motherboard is extremely important because it acts as like the central hub of your PC. Its function is to serve as a single platform to connect all the parts of the computer together. So if you think about the computer as like a human body, the motherboard is analogous to the nervous system because it sends signals to parts and coordinates the entire machine. If you look at on the picture on the right, you can sort of see what I'm talking about. There are slots for various components such as the CPU, RAM, and external ports, and these all fit into this one motherboard. They also have different sizes depending on how many ports or expansion slots the user needs. So the smaller the motherboard, the less customizability you'll have on your PC because of less slots. However, the price is also cheaper. And the biggest size you'll find on the market is a standard ATX, and then the medium size is micro ATX, and the smallest is the mini ITX.
So here we're gonna do a little crash course on CPUs. But before that, I want to say that it would be nice if you can absorb everything during the meeting, but not all of it is required for the lessons we were gonna teach afterwards. So don't feel bad if you don't get everything. If you have any questions, just ask us after the meeting or DM us on Discord or something like that. Also, we won't go into transistors, circuits, latches, etc., because they're too low level for us to worry about like in this club. We just hope that you get a better idea of how things works in computers. Okay, let's get back to the CPUs. So CPU stands for Central Processing Unit. You can call it the processor, and it's the main chip that runs your computer. Okay, the purpose of a CPU is to process data, do calculations, execute instructions, and basically tell the rest of the computer what to do based on stored programs and external inputs like keyboard presses or mouse clicks, etc. Next. Although modern day CPU have, wait. Yeah, okay. Although modern day CPUs have more components, there are 3 core parts of a CPU that are the most significant. Okay, the first part is the registers. A register is a tiny storage for data to be retrieved and or stored quickly inside the CPU. Registers have different sizes depending on the architecture of the CPU. So if you have a 64-bit CPU, the registers will be 64-bit large as well, or divide that by 8 bits per byte, you get 8 bytes per register. There are 16 general purpose registers for the 64-bit CPUs we use. By the way, those 64-bit CPUs we use belong to the x86 64 architecture. If a few of those 16 registers are used for special tasks, like storing the return value of a function or the base memory address of the stack. And the others are just used as places to store temporary values, operands of a math operation, arguments of a function call, etc. The reason why we have registers is that the main memory, or RAM, takes too long to access, and having something like registers that are close to the CPU improves the execution speed by several orders in magnitude. CPU also have cache memory, which are in between registers and the main memory in terms of distance and speed. Next up, we have the ALU, which stands for the arithmetic logic unit, like what it suggests. It handles logical operations like AND, OR, XOR, along with like math operations like adding, subtracting, multiplying, dividing, modular arithmetic, etc. Finally, we have the control unit, which serves as the command center of the CPU. It directs all operations of this computer and tells it what to do with itself. It executes programs and asks the ALU to calculate stuff, store the results in registers, etc. Next. So imagine you tell the operating system, aka the OS, that you want to execute a program. Maybe you clicked on it or something like that. The OS tells the CPU that this program should be run. Then this program is loaded from the hard drive into the main memory or the RAM, and then the CPU starts executing it. These fundamental operations, so there are fundamental operations that what the CPU does when it runs the program. Basically, it fetches the code from the main memory or the instruction cache. It tries to decode it and like identify what instruction it is, and then it executes it, and then this loop continues basically. If you're wondering what instructions are, they're basically basic operations that the programmer can tell the processor to do. They're the building blocks of all computer programs. It's like how cells are building blocks of life and how atoms are the building blocks of matter. It is possible to go even more granular than an instruction or a cell or an atom, but that's all you have access to as a programmer. It is the lowest level that you can actually use. Okay. CPU operations like fetching and execution, etc., runs on a certain time interval defined by the CPU's own hardware clock. This hardware clock produces electrical signals on a fixed time interval, and the pulse, the signal or the pulse itself is called a clock cycle. The time it takes to get to the next pulse is called the clock period, and the number of pulses per second is called the clock speed, or the frequency, measured in hertz. So when the CPU has a frequency of 3.5 gigahertz, it really means that the clock pulses 3.5 billion times per second. There are two types of CPUs that differ in the type of the instructions they use. One type is called the complex instruction set computer, or CISC. CISC allows for complex instructions that might take a long time to execute. The benefit of that is that it keeps programs short and succinct, which saves storage space. The downside is that the CPU becomes more complicated as it has to handle these complex operations individually, causing the clock cycle to slow down. And the other type is called RISC, or a reduced instruction set computer. So instead of using a complex instruction in CISC, RISC uses multiple simpler instructions to accomplish the same thing. Basically splits them up and just don't use that complex instruction anymore. This makes the RISC processors simpler and quicker, but the size of a program becomes much larger because now it has to store a lot of simple instructions as opposed to one complex instruction. And then later, people modded CISC so that on the surface, it still supports complex instructions, but inside the processor, the complex instruction is broken down to smaller operations called micro-ops. It's kind of similar to RISC, but the only difference is that you still use complex instructions. Okay, this practice of breaking down CISC instructions into micro-ops within the processor is called microcode, and it is used by countless commercial CPUs. CPUs also differ in the way that they execute instructions. So a single cycle CPU means that it only executes one instruction per clock cycle. It keeps the CPU simple, but extends the clock cycle to the longest performing instruction, which is pretty inefficient because it only spends one clock cycle for all instructions, and it wastes extra time for the shorter instructions because the CPU is basically doing nothing after the short instruction is done until the next clock cycle. A multi-cycle CPU, on the other hand, allows the processor to execute an instruction in multiple clock cycles. This means that instructions which previously took the same time to execute because of the one instruction per clock cycle rule, now it has the chance to take less time to execute because the rule no longer exists. The downside is that it makes the CPU much more complex to implement, and yeah, that's it. But there is a more superior way to execute instructions called pipelining. Next. We previously have the so-called subscalar CPUs, and with those you have to use the inefficient single cycle or multi-cycle design because it can only execute one thing at a time. So one example of that is the image on the top right corner. So each row is like an instruction, and it can only run one at a time. So nowadays we have modern scalar CPUs, which uses a technique called pipelining. Instead of executing one instructions at a time, the instructions are split into different stages. The exact number of stages can differ between processors. So this splitting allows for simultaneous execution of instructions. Different parts of the CPUs can be used at the same time, as opposed to the single cycle design in subscalar CPUs where only one part is used at a time. This increases the number of instructions that can be run per time interval, aka the throughput. It also makes the clock speed faster by a factor that is the same as the number of stages. So for a scalar CPU, as long as you're not running the same two stages together at the same time, you'll be fine. There are also superscalar CPUs that can execute the same stage simultaneously by duplicating hardware parts, etc. You can probably see them in supercomputers. Just a side note, CISC CPUs are harder to pipeline, and some are not pipelined at all. But microcode CPUs and RISC CPUs are far more pipelined than the CISC ones. So below we have an example of a basic or classic 5-stage instruction pipeline. So not all instructions have to do all the 5 stages. So for the shorter instructions, it just skip over some of them, and for the longer instructions, it probably uses all of them. And so the first stage is IF or instruction fetch. So during this stage, the CPU obtains the instruction to run from the instruction cache or SRAM or the main memory when necessary. The CPU knows which instruction to fetch using the program counter, which is not a register. The program counter, or PC, is, by the way, it's also called the instruction pointer in the actual. So it's the instruction pointer is the name of the actual register in CPUs we use today. Okay, so the program counter stores the memory address of the next instruction to execute. So after the instruction is fetched, the program counter is incremented to the address of the instruction after that. Okay. So next up we have ID, which stands for instruction decode. this is a stage where the control unit check for which instruction was read, and then it sends the necessary control signals. If the processor is microcoded, it might do a bit of logic to figure out what micro ops it should use. For certain architectures, the register used in the instruction is read in the stage as well. So the CPU might also treat branches or jumps differently here. If you don't know what branches and jumps are, we'll talk about them later. So after that, the command after that, it's the execute stage, which is where the actual execution happens, and it usually does stop with the ALU and handles multi-cycle instructions. And then we have the memory access stage, where the memory is accessed if necessary, like loading from memory, basically reading from it, or storing something into memory. If the instruction doesn't need to do that, it's simply skipped. And the last part is the register write back, or the WB. In this stage, the control unit writes to the registers if there's a need for it. Okay, that'll be it for this slide. Okay, one of the crucial features of the CPU is parallelism. Oh, whatever. It's the ability to run multiple things at the same time. Wait. Okay. There are two ways we can do this, and they can be also used together. The first one is instruction level parallelism, or ILP, which focuses on how fast instructions can be executed, and then so it needs better hardware in order to improve it. And there's also task level parallelism, or TLP, which focuses on how many tasks the CPU can run simultaneously, which doesn't require a speed boost, but uses some like special techniques. So it is possible to do task level parallelism because we have instruction pipelines, which allows us to run multiple instructions in parallel. The task itself can be a process, which is a formal term for a running program. Like if you run Chrome, that is the same thing as starting a Chrome process. A process can also have multiple threads that run in parallel. For example, let's say you're running Word from the Office suite. So one thread can handle your typing and stuff, or formatting. Another thread can like print your document, and then another can be uploading your current document and auto save it to OneDrive or whatever, and so on. So this behavior is known as thread level parallelism, or basically multi-threading. We'll go into too much detail here, but basically your operating system remembers what is going on in one thread, it saves it, and then quickly switches to another thread and runs that thread for a bit, and then it switches back, and so on and so forth. Okay, so this is basically what allows you to this is basically what creates an illusion of simultaneously executing things. It's not really simultaneous. It's just that it does this thing for a bit and then switches to another. So it switches so fast and you can't even recognize they're being switched. So so as long as the CPU is robust enough, you won't notice it. Okay. Wait. Okay, so here's some very basic assembly. Okay, before we start, so be aware that there are two types of syntaxes for like the x86, assembly. So there's the Intel syntax, which I will use here because it looks nicer, and then there's the AT&T syntax, which is like pretty different in notation wise. Okay, and some people hate it because it looks ugly. But yeah. So if you remember from earlier, we basically use registers with the instructions, and so some for 64-bit CPUs, and then basically the x86 64 architecture, we have 16 general purpose registers. So like RAX, RBX, blah, blah, all the way till R15. And then, so you can also access the lower 32 bits of these 64-bit registers through like another, basically other names. So if you have RAX, that you can access its lower 32 bits through EAX, and you can also access its lower 16 bits through AX, and then the lower 8 bits through AL. So they're basically the same register, but their size is different. They're looking at different parts of it. Okay, and for the basic instructions, we have the move instruction, which is basically so we basically move a B to A, and then it's basically copying. You're not really like moving something from B to A. B stays the same, but A gets the value from B. And then there's also the jump instruction, and then there's it basically like redirects the current like, okay, it sets the next instruction to something else. So instead of going from instruction 3 to instruction 4, if you have a jump instruction that says jump to 5, it just sets the like program counter to 5 and then runs from there. There are also variants of the jump instruction, like jump if not equal or something like that. So these basically test if the condition is satisfied. If it's satisfied, then it jumps. If it doesn't, it just keeps like executing as normal. So that's what allows branching to happen. So branching is like if statements in like real code, etc. And you also have the call instruction, which is, so if you know programming, you know that there are functions and you can call them. And then the call instruction basically like it's the same as the jump instruction, but it does a bit of extra stuff which we won't cover here. So the call instruction, it jumps to that function, it does a bit of that thing, and then the function returns and it goes back to the next instruction. And there are also the test instruction. So it basically produces an it basically does an logical AND operation on the operands. So, and then it stores the result in the flags register. So the flag register has a group of, I don't know, like it's a group of registers kind of. So you have so for example, you can have the non-zero flag. So if the last test instruction or some other like logical instruction is like non-zero or something, the processor sets it to 1. So you can yeah, we'll explain that. So if you don't get it, we'll go in depth in our later binary exploitation section. Okay, which is probably later in the year. Yeah. Okay, next. Okay, so a bit of extra stuff. So besides the main CPU, Intel processors also have this creepy thing called the management engine, which is a separate processor from the CPU. Okay, the management engine has the highest privilege on your computer. It is colloquially known as the ring -3 privilege. It can do it basically means that it can do anything to the computer and completely bypasses the operating system. For example, it has full capability to read the device memory, basically the RAM, and send whatever is in there over the internet. And for this reason, the ME has been an attractive target for all like hackers and stuff. It also runs whenever the motherboard receives power, regardless of whether you booted up the computer or not. Intel denied that they install backdoors in it, but you never know. If the government wants to install backdoors, you'll probably start here. AMD also has something similar called secure technology. Yeah, that'll be basically it for a CPU section.
Okay, so the CPU is extremely complex, but it can't do anything without communicating with other components of the computer. So a bus is basically an internal high-speed connection that allows the processor to do this. There are 3 types of buses. The first is the address bus, which determines the location in memory where the processor will read data from or write data to. The data bus contains the actual contents and information that has been read from the memory location or to be written into the memory location. and the control bus manages the flow between components, indicating whether the interaction is a read or write. Next slide. And the computer has different ways of storing data as memory. There are two different types of memory, RAM and ROM, but both are present in your computers. RAM stands for random access memory, and it's a form of volatile memory that temporarily stores the files you are working on. When you restart or shut down your computer, the data stored in RAM is erased, and this is due to the fact that the information is stored electrically on transistors, and when you shut down the PC, there's no electric current, so the data will disappear. ROM is non-volatile memory, which means that the information is permanently stored on a chip on the motherboard. So this type of memory does not use an electric current to save data. Instead, data is written to individual cells in the chip. And ROM memory is used for parts of the PC that don't change, which are things like the boot up portion of the software, so BIOS. Next slide. The main function of a disk is to act as a storage space to store data for long term. Examples of data in the disk that can be stored are computer operating systems, applications, documents, and personal files. HDD stands for a hard disk drive, and a hard drive is essentially a metal disk with a magnetic coating. And attached to the disk is also a read-write head, which uses a thin horizontal magnetic blade to read or write data. HDDs are generally less expensive because they are a lot slower than SSDs. A SSD stands for a solid-state drive. Solid-state drives perform the basic function as a hard drive, but data is stored on interconnected flash memory chips that retain the data even when there's no power flowing through them. So this makes them a lot faster than HDDs, which in turn makes them more expensive. Graphics audio network cards are components that you would add onto the PCIe slots of a motherboard, and these cards enhance your PC. A graphics card is a piece of computer hardware that produces the image you see on a monitor. They are able to do this through processing, which converts data into a signal that the monitor can understand. All the hard work is done by the GPU, or graphics processing unit. There are two different types of graphics cards. Integrated GPUs are built into the motherboard, so it saves money and is effective for less resource-hungry tasks, such as just simply browsing the internet or watching movies. But this also means that they are less powerful than discrete GPUs, and a discrete GPU is installed on the motherboard as an extra component. This makes them interchangeable and allow users to easily modify their systems by upgrading the graphics cards. But since a discrete GPU is a separate component built entirely for rendering calculations, it's much more powerful, and this makes it more expensive. The sound card is an expansion card that allows the computer to send audio information to an audio device like speakers or a pair of headphones. However, it's not a vital part of the computer to make it work. Most of the time, the sound card is just built into the motherboard, and that provides sufficient audio quality for regular users. The only time where you would need like an integrated audio card is if you were like a musician that does a lot of audio processing on the computer. And a network interface card is installed in a computer to provide a dedicated internet connection to the computer. It allows communications between computers through a LAN network, as well as communication over wide area networks through the internet protocol. And most laptops and pre-built computers have an internal network card integrated into the motherboard. However, if you have like a custom-built PC, you probably had to install an external network card using the PCIe slot on your motherboard in order to connect to the internet.
All right, so Jason and Zenkai covered over like hardware of your computer and like kind of physical architecture, but I'll be going more into depth on firmware, which sometimes is forgotten about, and it's kind of this like middle guy between software and hardware. All right, so basically computer firmware is actually, so computer firmware basically connects your software to your hardware, and it's this kind of low level connection to your hardware, and it's kind of like a backbone or intermediary, and this hardware or this firmware that's usually coming in with your computer or whatever devices you have, they're tailored for specific parts, and so when you get a computer, usually you don't touch anything with the firmware, and it just connects to your hardware it just connects to your hardware basically. and is actually so like what Jason was talking about before. This is actually some data. So firmware is actually data held onto some kind of hardware chip or process or hardware chip or something, and it's held in these non-volatile memory areas like ROM or read-only memory, like what Jason was talking about. And there's also two additional other ones, EPROM and EEPROM, and these two are basically kind of a more advanced version of the ROM. And so ROM, the thing is, it's read only, so you can't edit it, you can't write to it. And so when you get a computer, this ROM usually comes in with the chip, and the only way to actually replace it or to update it is to actually physically take it out and replace it. But EPROM and EEPROM were introduced a bit after. So ROM was introduced in like 1956, but EPROM and EEPROM were introduced in 1971 and 78. It's like 20 years after. And they were actually able to flash it or basically change, or you can reprogram it. And so for the EPROM, they do it by ultraviolet lights or ultraviolet, and they use light to actually reprogram it. And EEPROM, they use like electrical voltages, like how you normally write to memory or something like that. And so this firmware is literally everywhere in most of your electronics. If it's a phone, it's a computer, even something like your dryer or your washing machine or your dishwasher usually has firmware in it, and it allows communication to the hardware. And so on your PC, there's also a lot of common examples like BIOS, like Jason's talking about. BIOS is usually written on your computer so that when you're booting up, that you're able to boot up your computer, and it's able to run an operating system. And so you also have storage. So you have firmware to communicate with your storage from a so if you had a computer, let's say you had some software that saved a file, you'd have to use firmware to actually connect to your hardware and to your memory to save that file and give it instructions. And you also have like graphics. So your graphics card also has firmware. And if you want to look at more, you can just check out if you have a Windows computer, there's Device Manager, and you can go on Device Manager and look around. And there's a bunch of devices, things like your mouse. If you have a gaming mouse and advanced gaming mouses, now they definitely have firmware to communicate with your computer. And so so right now I'm actually talking as if firmware is different than software, and in actual sense firmware is software. But in today's world, when you think of the word software, you think of like Microsoft Word, you think of Google Chrome, you think of games that you have. And so in like the culture today, you think of those kind of things, and you don't think of software as just data and like and so firmware is actually considered software, but because firmware is just a bunch of data about how a program should run, how you connect to, or not how a program should run, how you connect to a hardware device, and kind of configures how the hardware device works and how you can communicate to it. And it is software, but compared to what we have nowadays and such a high level of software and something like a game or browser, that kind of software usually if we introduce firmware as software, people will think of it as like that. But instead, it's a really low level. It's actually the lowest level of connection to. It's the lowest level of software. It's the most kind of. It's closest to hardware. So all this other software is built off of it, and so that's why they like to call it firmware and not software. And so yeah, so hardware is like hard, it's like it's physical stuff. Software is kind of like just data. It's kind of like it's more conceptual when you think of it, and it's more of like something abstract. And so firmware is like in the middle, and it's kind of firm, or it's kind of hard, so it's firmware. All right, so then so this firmware usually is really small actually. So software programs you might have might be even a couple gigabytes, but software is only a couple kilobytes, maybe in the double digits or triple digits, but it's usually really small. And this image since it's stored on non-volatile memory, it's kept, and when you turn off your computer, it's still there. turn it back on, it's still there. And it's rarely touched by users. You rarely update it, or you never update it, or sometimes you have to bring it to PC shop to replace it or whatever. And how you update it is using flashing, but you really only can do that for EPROM and EEPROM. ROM is you have to physically replace it, so you can't really flash it. And flashing is where you basically just wipe out all the data and then you put in some new program. And the data is written in C, the C language, so it's pretty darn close to assembly and machine language, and so that's why it's so close to your hardware. Okay, so yeah, firmware, that's basically it for what it is. So it's kind of a connection between your hardware and your software. And since we're in cybersecurity club, we obviously have to talk about hacking your firmware. So people have so usually this firmware is provided by a manufacturer, but people have tried to change it, to break it, to tailor it to their own specific needs and make custom firmware. And so one of the examples is Rockbox, and it was basically a custom firmware that was made for media players like your MP3 or your iPod. And there's a bunch of people out there who've messed around with things or messed around with firmware and changed their functionality for either the better or the worse. And I think one of the examples is running the game Doom on iPods. So yeah, for iPods are kind of irrelevant now, but back in like 10 years ago, iPods were kind of a thing. So then, yeah, there's firmware that was kind of changed there so that a game could be run on it. All right. So now let's talk about exploits. There's been a lot of exploits. So people have tried breaking into firmware, and hold up. All right. So exploits. There's been a large since like what Zenkai talked about with the Intel chip and the -3. There's also firmware is really close to hardware as well. And so if you can exploit this, you almost have a direct connection to the firmware. You don't have to bypass anything. And that's why people are really interested. And so for this firmware, it's open source, and usually this code is released by manufacturers so that if there's vulnerabilities, these exploits can be patched. But there has definitely been firmware hacking and trying to access people's computers. And one of the exploits is using USB devices. So people taking USB devices and changing their firmware, and then you plug them into a computer, and it could screw up the computer pretty bad, and like make it track data or even run unauthorized tasks and things like that. And so one of the exploits is actually from Equation Group, a Moscow based group of like hackers, and these guys created a Trojan, and some people think that they worked with the NSA from America to break into stuff and create this exploit. And so yeah, you really don't know when you might be getting hacked with the firmware. And so they found a way to basically write data into your hard disk and your memory that even if you normally you try wiping your own disk, it doesn't get erased because it's put in certain areas. And yeah, so NSA might use this to track us. We never know. And yeah, it's kind of a security risk, or it is a security risk. And so yeah, there might be a lot of hacking going on, or there's definitely people looking into firmware and looking in it's kind of a sweet spot because you can get such a close access to your hardware. And yeah, so I think that's about it for firmware and the overall meeting. So we kind of covered a lot today, and we did go over time, but so we went and discussed mainly hardware, and then went to firmware, and in the future we'll definitely talk about the software aspect of it. So if you guys have any questions or you want to join, be sure to join the Discord or look around in the wiki. And yeah, that's basically it.